final session. We've got Yingzhen Li from Microsoft Research at Cambridge, and she's talking about Bayesian neural networks. So, up to you.
So hello everyone, it's my great pleasure to be here. In fact, I was actually quite surprised that I was invited for this session because I'm going to talk about Bayesian neural networks, to you guys that is a fan of GPs, okay? I mean, I did quite a lot of Bayesian neural networks during my PhD, and now at Microsoft Research Cambridge, I had some projects that actually also use Bayesian neural networks as well. Bayesian neural networks is kind of like putting prior distribution on neural networks, and then you do sort of like inference, a lot of approximate inference methods in the weight space, and then you do some sort of, say, predictive inference, uncertainty quantification. But today I'm going to tell you, about my work on Bayesian neural networks with some sort of introduction and also the connections of Bayesian neural networks to GPs. And let's see how it works. Okay, let's say I want to do image classification. Different neural networks are very good for image classification. So let's say I want to classify different types of cats. And in this case, I have X as the input images and Y as the output labels. So I want to build a neural network with some parameters W so that I can parameterize the probability distribution of the labels given the inputs as kind of like a softmax transformation of some function. So you learn a lot of like non-parametric things in this summer school, but this neural network is actually a parametric model where you explicitly, parameterize the function in this specific form. You have kind of like layers of, say, linear transformation plus kind of non-linearity, and then you do this kind of these things one layer, but each by one layer. Okay. So you can see this is basically just a very simple linear transformation, and this is just non-linearity, okay? So a typical deep learning solution right now is basically just you have a big data set, and then you feed this neural network to find the best parameter with something called maximum likelihood estimation. So essentially, this tells you that given a data set, I'm trying to optimize the neural network parameters so that it will maximize the probability of the data, of the observed data under the model. Okay, so this is the usual deep learning solution. You basically usually run, say, SGD and then run for some time, and then hopefully it will converge to some good solution, and then you use this sort of point estimate to do prediction when you have new data. Okay, so this is the deep learning way to do things and the daily job for deep learning engineer. Okay, so in this summer school, I hope you are all Bayesian. So instead of doing kind of point estimate, we are going to do some sort of Bayesian solution for this one. And in this case, instead of like treating the parameters W as some sort of deterministic point estimate, we are going to treat this W, the collection of weights, as a random variable, and then we are going to put a prior distribution, say for example like Gaussian distribution on the weights. So now we have the kind of prior distribution over the weights, and then we can have this kind of likelihood term of the weights under the kind of like observations. So by Bayes' rule, we know that we can compute the posterior distribution, which is basically just the prior, proportional to the prior times all the likelihood terms. Okay, so if you can compute that, then in prediction time when you have new data X star, then you basically just do this kind of like Bayesian model kind of predictive averaging by sampling some sort of weights from kind of compute the expectation of these kind of conditional probability under the posterior. Okay, so this is kind of Bayesian predictive inference if you are going to do Bayesian neural networks. In practice, the posterior is almost always intractable. Many of the kind of Bayesian models have this problem. So it is also the case for Bayesian neural networks. So in practice, usually what people do is to first find some sort of approximation. I'm not going to talk about how this is done, but usually people just find some approximation Q of W that approximates the exact posterior, and then in prediction time, instead of doing kind of like the posterior averaging using the exact posterior, we are going to use the approximate posterior, and we are going to do one more step, which is Monte Carlo approximation. So this means once you have your approximate posterior in prediction time, you first sample a bunch of weights from your approximate posterior, and then do this kind of empirical averaging to compute the probability of the predictive label given the new data point. Okay, so this is a super quick introduction of Bayesian neural networks. I hope this is clear to you. Definitely ask me questions if you have. So let's see what kind of applications that you can use Bayesian neural networks. So I mean, if you only want to do some sort of like good prediction, you only care about prediction error, then basically probably neural network is enough for you. But if you want to do something more like that, things involve uncertainty, then you need some sort of way to quantify uncertainty, and Bayesian principle is a kind of good way to do it. So I did this kind of little project 2 years ago with Yingzhen, who is now at Oxford. So in this project, we are basically trying to see whether we can use some Bayesian neural networks to kind of tackle some sort of like adversarial examples. So back in 2017, the adversarial example things is getting more and more popular, and people basically just apply some sort of perturbation that is kind of specific designed for the victim model, so that the perturbed kind of like the corrupted example can actually fool the classifier to give the wrong result. Okay, so this is actually a very simple attack called fast gradient sign method, where you can think about these kind of x-axis as kind of like the strength of the attack. So close to the right is kind of like the stronger one, and the y-axis is kind of like the accuracy of the model, given these kind of corrupted images. So in that time, we compare the deterministic neural network with, say, Bayesian neural network with other kind of inference methods. In that time, we are using alpha level to do that. So basically, the observation here is first that if you compare like the accuracy of the, say, the models given the same strength of attack here, we can see that at least these are Bayesian neural networks in the color curves. They are more robust comparing to like the deterministic neural networks. But more importantly, you can actually compute some sort of uncertainty estimate of like your prediction on your prediction. So we compute the predictive entropy of the model, given this kind of corrupted input, and we see that when your input is moving away from the kind of like data manifold, you can basically see that the Bayesian neural network is kind of getting more and more uncertain, while the kind of like the deterministic neural networks, well, it has some bumps, but finally it kind of goes back to kind of a very confident region. So that basically means the deterministic neural networks makes wrong predictions in a very confident way. Bayesian neural networks, they are more robust, and at the same time, when they make wrong predictions, they actually are uncertain about it. Okay, so that's one application. So other applications, neural networks are kind of used a lot in computer vision problems. This is a typical computer vision problems where you're going to do like image segmentation. So if you use kind of deterministic neural networks, then this is the kind of like the third column is kind of the typical solution you will get. But you won't get this kind of like the fourth and the fifth column with deterministic neural networks. So with Bayesian neural networks, you can actually get uncertainty output, and you can even decompose your uncertainty estimation into something called aleatoric and epistemic uncertainty. Okay, the aleatory one is kind of like the one for noise, and epistemic one is kind of like the uncertainty when you have few data. Okay. So some other kind of say real-world application that people really care about uncertainty is some domain like healthcare, because people are going to use kind of like the prediction outcome from your system to make some sort of like decision. For example, like make an invasive treatment to the patient. So this can have kind of some very bad outcome if you don't do that in a good way. So that basically means when you're trying to kind of say rely on the system to make decisions, you really want the system to tell you how confident it is for kind of like the recommended treatment. So some colleagues at UCL and also in collaboration with Microsoft, they are doing this sort of like super resolution problem for medical imaging, where they take these kind of say fMRI scans and then try to enhance its quality. So yeah, there are a lot of kind of deep learning methods that based on GANs that can do super resolution that basically gives you this result. But you also need uncertainty, which means you are going, in this case, they are using a Bayesian neural network to output not only kind of like enhanced result, but also kind of like the uncertainty map of this enhanced result. Okay, so I've talked about a lot of applications. a bunch of applications. And neural networks are great for kind of vision and also like speech recognition, also NLP applications. But why we are talking about Bayesian neural networks in this summer school? Apart from the kind of like the practical good usage of neural networks, why we are talking about this? So in the rest of the talk, I'm going to talk about three things. So I think first thing, kind of like the Bayesian neural networks with mean field prior has the kind of GP limits. I think you heard a bit about it in Neil's talk today about deep GPs, but he skipped a lot of details on kind of the derivation. I'm going to derive this result step by step. Okay. So the second one I'm going to talk about is basically GPs. Although it's theoretically great, in practice it is kind of like not that scalable because you have kind of n-cube complexity. So you need to do some sort of approximate inference on that, and a particular type of approximate inference algorithm actually connects GPs back to Bayesian neural networks. Okay, so these two are kind of like the results that are kind of like well known in the GP community. And the third topic is related to my recent research. I'm going to talk about like some other approximate inference methods for Bayesian neural networks that takes inspirations from GPs. Okay, so let's start these kind of classical results. So before I tell you the connections, the GP limits of Bayesian neural networks, let's get a very quick refresher on kind of like the central theory, the kind of central theorem it's applied. So this is kind of like the Stat 101 thing, central limit theorem. It basically tells you that if you have a random variable x that is distributed according to P of x, then you can use kind of like the population mean to estimate its mean, right? And the population mean itself is also a random variable. And when you have, say, infinite number of samples in this population, then the population mean will converge in distribution to a Gaussian random variable with the right mean and kind of like the scale variance. Okay, so this is central limit theorem. So let's go back to Bayesian neural networks. So in this case, I'm considering just one hidden layer Bayesian neural networks with this kind like a lot of definitions, but let's try to draw something. Maybe it's better to draw something. So you have the input x, okay, that connects to a lot of units. Okay, let's just draw 4 units to start with, and then you have the 4 units connected sum up to the output f. Okay. So as I said before, we are going to treat those kind of parameters as random variables. So we are going to put a prior distribution over the parameters. And in this case, we are going to do mean field prior or vectorized prior. So all the parameters here are collected in W, and they are, the prior distribution is vectorized in this way. So the first layer's weights and the bias is independent with the second layer's weights. And also for the first layer, you want, say, the connections into this different units, the prior distribution to be independent. So let's say, for example, x is 2 units, then you have a lot more connections like this, and also this. So I'm just so this second equation basically says that the prior distribution over these 2 weights is independent with the prior distribution over these 2 weights. Okay, and more importantly, we are going to put the same prior for all these kind of different sets of weights. Okay, for example, you can put like the Gaussian prior on this set of weights and also Gaussian prior on this set of weights and make them to have the same mean and variance. Okay, so this is the mean field base. This is the Bayesian neural network with mean field prior that we are considering here. Okay, so because we have the kind of like the same prior for each connection, and also the weight bias here, then it basically says that when you given the input x, you have these units, this hi, and these units to have the same distribution, and they are also independent, right? Because you assume this input is kind of fixed, and also these weights, they're independent and they have the same distribution. Okay? So basically, this means that these two units are, or maybe I should say all these units, are IID samples from the same distribution, which is implicitly defined. Okay? So the same thing, we also apply this same thing again, because we assume that the second layer's weights is independent with the first layer's weight. And we also assume that this connection has the same distribution as this, and also factorized. So when you multiply these kind of weights with the hidden unit output, also do the same thing for this, then you find out that the output here, they are also kind of like IID samples from some implicitly defined distribution. Okay? So that basically means that this f of x is basically just the sum of some IID random variables. Okay? So we are almost there. So now let's make a bit more specification of what the prior of the second layer weights looks like. So if you make like the second layer's weights prior to have 0 mean, and its variance has some proper scale that is scale kind of like 1 over m, where m is the number of units, then you can basically just compute kind of like the mean of the function output, which is just 0. And the variance, which is basically just the variance of the second layer weights times kind of like the second moment of the hidden units, and then you apply this kind of like the essentially Me theorem to tell you that when m kind of number of units goes to infinity, then this thing converges to some variance, right? Okay, you can do a similar thing for the covariance as well. So you basically just take the two different inputs x and x prime, compute the covariance. You basically take all the previous assumptions. You can actually work out that when n is finite, the covariance is this form. And when you kind of say take the number of hidden units goes to infinity, then you also converge to some covariance function. Okay. And also, kind of like the central limit theorem tells you that we have like the random variables fx and x prime converges in distribution to a Gaussian random variable with kind of like the previously defined mean and the variance such like this. And because this thing holds for any x and s prime, basically it just tells you that now if you take a one hidden layer Bayesian neural networks with this kind of particular mean field prior structure, and then make the number of hidden units goes to infinity, then you have like the output function distributed as a GP. Okay? So this is kind of like the detailed derivation of this kind of Bayesian neural network limits result to GPs. So I hope this is super clear to you. And I mean, I want to do these kind of derivations because in the later topics we will see lots of similar things. Okay? So there are a few extensions of these results. Yes?
So quick question. Earlier you mentioned that the output can be considered to be IID. But then there is like two layers that are fully connected. And in my mind, this introduces correlations.
It is only one hidden layer, right? So the input is some sort of like fixed input. It's only one hidden layer. Oh, if you have two hidden layers, then there are something more complicated.
Sorry, yeah.
Okay. Yes?
One question. So now we talked about the prior, which converges to a GP for infinitely many hidden units.
Mm-hmm.
But then, so what about the posterior after training this thing? Is this also the Gauss? Because the central limit theorem assumes that we have IID distribution.
Yeah.
But then when I train my the parameterization of my weights, which all have different means and variances, then they're not identically distributed anymore. And so what do I get then? Like, is the posterior also related to the Gaussian process posterior?
Not quite. You are correct that if you have like say a finite number of hidden units, even when this kind of m is super big, even when the prior is very similar to like the GP, so the posterior can be a bit different.
Okay.
So yeah.
So but there's also something like central limit theorem for, I think, like independent variables, but not identically distributed.
Yeah.
No, so this kind of holds maybe then. So, okay, but there's less.
The problem is that I think in the posterior you have correlations between units.
Okay.
So even not identically distributed, even kind of like the independent things is not quite true.
Yeah, okay. Yeah.
Okay, so this is only holds for prior. Okay.
Yeah, okay. All right.
Any other questions?
Less of a question.
Yes.
Comment. I think that like going off of your question just now, I think that the neural tangent kernel is a related result to this that corresponds to a network setup of this style after having been trained using stochastic gradient descent for an infinite amount of time. And it's also a Gaussian process structure, but with a different kernel structure.
Okay. Okay, let's carry on. So, so this result is kind of like the result from Rafa News PhD thesis. I believe this is almost like 30 years ago. Okay. There are recent attempts that try to generalize this result because people, start to ask, okay, so, right now we are using deep neural networks, which is neural networks more than one hidden layer. We are using many hidden layers. So, and we are also making kind of like the hidden layers very wide. So, if you make kind of like your deep neural network also wide, would that give you something similar to GPS? These two papers basically gives you kind of an affirmative answer. So their result is actually very similar to the kind of like the previous reference results. They also assume this kind of mean field prior because they want to use this kind of central limit theorem result. And they make some sort of a bit assumptions on the activation so that they can control kind of like the moments. Okay, and these two papers, they use different proving techniques. And this paper from Google Brain, they say they are going to kind of like put kind of like the limit, to put each layer to limits by, say, I put the first hidden layers, number of hidden units to kind of infinity, and then I put the second layer, and then I put the later layers. So this paper, Alex Matthews, so he was in Cambridge previously. They say, okay, instead of doing this kind of layer-wise stuff, I want to kind of put the limits of all the layers simultaneously together, but they need to do some sort of like extra techniques. Okay, here I'm showing you the some sort of like the figures from this paper. So I believe that this Bayesian neural network is a 3-layer. It has 3 hidden layers. Each hidden layer has like 50 hidden units, and this is kind of like the GP fit given this kind of input data point and using the corresponding Bayesian neural network kernel. And this result is obtained from kind of Hamiltonian Monte Carlo sampling of the posterior weights, which is considered as kind of like the gold standard inference method for Bayesian neural networks in weight space. You can basically see that in this toy example, so they look pretty much the same. So at least these two papers, prove you in theory that when you have very deep and wide Bayesian neural networks with mean field prior, they are also GPs, and experimental result it also confirms this. Okay. So this year I clear, two similar group of people. They do the same thing again for CNNs. Yes.
So can you repeat that? Which inference strategy is the gold standard?
In weight space, the gold standard is Hamiltonian Monte Carlo. Okay. So yeah, so this is I cleared two groups of people trying to generalize these results to convolutional neural networks, and convolutional neural networks is, I would say that it's kind of like a specifically structured, fully connected neural networks in the sense that they apply these kind of like weight matrix to each of the kind of small patches of the images, so that you can basically see that the output is kind of like a 3D thing where they have the spatial output and also have the channels. And in CNNs, you can also think about the number of channels as number of hidden units in the fully contained neural networks. So their result basically says that, okay, if you still use mean field prior okay, for the CNN weights. And then you made the number of, say CNN channels go to infinity. You also converge to a GP with a specific kernel. I think this paper, they also generalize these results to ResNet, where ResNet is basically saying that you have a bunch of convolutional layers, and then you add a kind of a skip connection to the top. And then you put the kind of like the right prior on both the connection, or both the convolution layers and also the skip connections, and you can show that the kind of resulting limit is kind of also a GP with some sort of additive kernel structure, covariance matrix. Okay. So I think this result are actually quite nice because it gives you some sort of like interpretation of how this sort of like very deep Bayesian neural networks behave in function space. And like deep neural networks and convolutional neural networks are actually quite heavily used in modern, say, deep learning works. Yes?
Do these Bayesian scaling, this limit, have anything to do with the convolutional GP stat work, or is it unrelated? Is it specifically, yeah?
I think, I'm not exactly sure because I haven't actually read in detail of the convolutional GPU work, but I believe that the convolutional GPU work is trying to construct some sort of kernel that looks similar to kind of convolution, right? So this one is basically saying that I have a convolutional neural network. I basically just treat it as a fully connected neural network with some specific weight matrix structure. Yeah, I don't think they made the arguments, say, using some specific properties of convolutions. They basically just, showed you that this weight matrix has this structure, and then take the similar proofs as the previous works. Okay. Yeah, as I said, like CNNs and deep neural networks are actually, quite heavily used in, say, a lot of industrial applications. So I think it's good to, have these connections to GPs so that, GPs, if you made the right kernels, you can actually apply it to, say, image classification problems, feature classification problems, whatever. Okay, so that's the first part. So before I go to the second part, do you have any other questions? Okay, so I just kind of finished a detailed derivation of the results that Neil told you this morning. But I'm going to give you a second view of this, which is I'm trying to do approximate inference in GPs, and the way I do it will actually make the approximation much look like Bayesian neural networks. Okay, again, I want to motivate this problem. So you probably have seen this equation in some school. This is basically just kind of like the standard GP predictive distribution when you do GP regression. Okay, so you can basically see here you have this kind of matrix inverse involved in both the mean and the covariance term, and this kind of like the matrix here scales kind of quadratically as the number of input or number of the training data increases. And also we know that inverting a kind of full rank matrix has like cubic cost like this. Okay, so this basically means that if you want to do like exact inference for GPs, even for like tens of thousands of data, which is actually considered kind of small data sets in deep learning area, okay, then you can't do it because this has cubic cost. You need to do some sort of approximation in order to make it scalable. Okay, so I think probably this works. Summer school has to teach you about like say sparse GP methods or inducing point methods. So I think those are very good techniques. I'm not going to talk about that. I'm going to talk about another technique that tries to do approximate inference for GPs. So again, a very quick refresher to some other, maybe I should say, real analysis 101 stuff. Okay, so it basically tells you that if you have some sort of like real value functions, then you can basically do kind of Fourier transform of it, into transform it from say time domain functions to kind of frequency domain functions. And under some certain conditions, you can also do some inverse transformation. That basically tells you that these kind of time domain function can be computed as kind of like the sum of different quantities, these sinusoids with different frequencies. Okay, so this is kind of like the classical Fourier inverse transform result. Okay, so let's see how it relates to kind of GP approximation. So again, a kind of like classical result of in kernel methods. So the Bayesian theorem tells you that if you have a properly scaled translation invariant kernel, which basically means that your kernel only depends on kind of like the difference between your two inputs, then you can basically just represent the kernel as kind of like a sum of sinusoids, okay? So something to note here, because the kernel has real values, and you know this kind of say exponential of this thing has some sort of like say sinusoids in the imaginary part. So it basically means that kind of imaginary part is 0, so that you can rewrite this kind of like Fourier inverse transformation into this form. Okay. So also there is another result tells you that the cosine of x minus x prime can be rewritten in this way, where you plug in another variable b with the kind of uniform distribution in 0 to 2 pi. Okay, so this is the another approximation. So you plug in these two things into the theorem again. We rewrite a little bit. Okay, so it tells you that if you have a properly scaled translation invariant kernel, then you can basically write it down as the expectation of the product of two cosines. Okay, under some proper distribution. Okay, does that look like the neural networks? Okay, so in this 2007 Neuro paper by Rahimi and Ben Ratchett, so they use this theorem and then notice that, okay, I can do a multi-color approximation of this kernel matrix, so that they basically just take samples of W and B from this kind of corresponding distribution, and then compute this kind of multi-color estimate of the kernel function. Okay, so you can basically see that this is unbiased estimator, and when the number of samples goes to infinity, you have kind of like the exact approximation. Okay, so we are almost there. So I'm going to rewrite the result a little bit. I'm going to collect all of these kind of say multi-sample sinusoids or sample cosine functions into a vector. Okay. So I'm going to rewrite the approximation a little bit that tells you that the approximated kernel can be written as kind of like the scale version of some product of features. Okay? And from this insight, we can see that if we have a GP that has some kernel function, and then we can first, yes?
Does something like this work with not translation invariant kernels?
I mean, I'm not that familiar with that, but I think there are some kernels that you can do it, say arc cosine kernel.
So for polynomial kernel, a cosine kernel, they exist, but it's different. It's not through a frequency approximation. It's not the Bayesian theorem, but they use a different. So random features can be used for other kernels as well. So this kind of sampling approach of having the limit for infinitely many samples that they converge to the true kernel value, that exists for different kernels. But there's different methods, so different distributions just use different activation functions.
Yeah, I choose to present Bayesian theorem because it's kind of most convenient way to display things. But definitely there are other kinds of non-translation invariant kernels that you can do similar approximations. Okay, as I said before, you can basically just do an approximation to the kernel, and then we have this kind of multi-color sampling. And we notice that if you have this specific GP with this kind of approximated kernel, then you can write down an equivalent weight space view. Tells you, okay, the function f tilted equals to some sort of like weighted average of the hidden units, pretty much like this. And it tells you that the weight here is distributed as a Gaussian with 0 mean and the corresponding scaled covariance matrix. So you can basically see that now, if you do like say random feature expansion approximation for the GPs, then you go back to like a one hidden layer Bayesian neural networks again. And in fact, if you are trying to improve your random feature approximation by increasing the number of multi-color samples, this is basically equivalent to adding number of hidden units in your kind of single layer Bayesian neural network. So you can basically see that the previous GP limit result of Bayesian neural networks and this kind of Bayesian neural approximation to GPs are kind of closely related. Okay, so there are people that try to generalize this result to deep GPs. So now told you about deep GPs. It's basically just compositions of functions where those functions are sampled from the GP. So Tangbo has this kind of work on has this nice visualization of that. So this is basically just a data set where the input is two-dimensional, and then you want to use deep GP to do that. You can compare that like the kind of GP result and the deep GP result. You can basically see that if you make, say, a composition of GP layers, and then you can basically get better result compared to just using a single GP. So that's basically why people are very excited about like using deep GPs to model kind of non-Gaussian behavior in function space. Okay, so remember the previous result, we have this kind of like random feature expansion approximation result for GP kernels. That tells you, okay, I'm going to first approximate the kernel for each of the layer, and then I'm going to write it down in a way that's similar to Bayesian neural networks. Okay, you can do that for every layer. So that basically means for every layer, I will do this random feature expansion results with, say, the selected number of random functions of random samples, which means the selected number of hidden units. And here, you are going to approximate kind of like the joint distribution from a deep GP with the joint distribution from a particular structure of Bayesian neural network. And what I mean by particular structure of this Bayesian neural network is that it is not kind of like wide in every layer. It has this kind of like bottleneck structure like you have seen in Neil's talk. So you're going to have one layer that is very wide, and then come followed by a kind of, say, a bottleneck layer, and then go to the wide layer again, and then go to bottleneck. So, I mean, the previous result from Matthew et al. And also Lee et al. Tells you that if you're going to make this kind of layer to have, say, infinite number of units as well, then it just goes back to GPs. So that's basically why you need this kind of bottleneck structure in order to make kind of like, say, non-GP behavior in function space. Okay, so these guys did this work, and they write down this view, and then they are going to do kind of like approximate inference in this kind of, say, weight-based view of deep GPs. Okay, so this basically means I have a deep GP. I'm going to approximate the predictive distribution of a deep GP with the predictive distribution of the corresponding deep Bayesian neural network. Okay, as I said before, the Bayesian neural networks, you also have inference problems. So we are going to further approximate it by some sort of approximate inference algorithms where you're going to first approximate the posterior of the weights by some approximate inference algorithm, for example, like Bayesian inference. And then in prediction time, you sample some weights, compute the empirical average of the condition distribution, and then use that to approximate the all the way through here, the deep GP predictive inference. Okay, so yeah, that's the results for like the approximation methods of GPs, which also has kind of nice connections to Bayesian neural networks. So I hope this convinced you that Bayesian neural network is still very interesting, and you should look at it. Okay. So before I go to the last part of my talk, so any questions? Okay, so the last part of the talk is something related to my recent research. So, I mean, previously I did quite a lot of Bayesian neural network approximate inference methods, but I did all of these things in weight space, which means that I'm going to kind of like do some sort of variation inference or sampling methods to get kind of like the posterior distribution of the weights, and then I use the kind of weight distribution to do, say, predictive inference. But there are some problems with kind of like weight-based approximate inference methods. So for example, we had a very recent work that just, we put the archive preprint last week that tells you that if you do kind of like mean field approximation in the weight space, and your data has this kind of specific kind of like clustering structure where you center the data with kind of center 0, then if you use kind of like, say, ReLU networks, then your approximate inference with mean field approximation cannot represent the in-between uncertainty at the same time as you feed the data well. So you can basically see this comparison that tells you, so this is kind of like the GP fit. So in this case, you can see you have some sort of like good mean fit and around kind of data regime, and in the kind of like the in-between part, you also have some decent amount of uncertainty. But if you look at this kind of like Bayesian neural network fits with mean field version inference, yeah, you can get the fits here, but you can't get uncertainty. Or in another way, you can get uncertainty, but you can't get at the same time kind of good fit around the cluster. So this, we also have some sort of results for Monte Carlo dropout. Well, MC dropout is in the corresponding posterior is not mean field, but it also has its pathologies. So we prove these things. No, this is kind of some theoretical proofs. It is not simulation results. This is proved to be wrong. So that tells you you have some problems with weight-based inference. You need to use, say, more sophisticated techniques. But even when you think about, say, more sophisticated techniques in weight space, so how does it actually look like in function space, right? So for example, in weight space, you have a lot of symmetries, because I can basically, if you have the same prior distribution here, I can basically just swap the nodes. That gives you the same function, right? So that basically means the posterior, in this case, has a lot of symmetry modes. And it is unclear whether you want to actually do kind of, say, multimodal weight space posterior approximation when you only capture the same symmetry mode, right? So yeah, there are a lot of questions that is not kind of well answered in weight space inference for Bayesian neural networks. So instead, I think in the recent kind of research, we want to look at like how we can do some sort of like approximate posterior inference for Bayesian neural networks where we actually do this inference in function space. Okay, so this is a recent work by Charles Marceau. He is a PhD student with Miguel Hernandez Lobato in Cambridge. I collaborate with them for some of the work. Okay? Yes?
I thought MC dropout, I might be mistaken. I thought MC dropout stochasticity only came in the predictions because the weights never change. It's just the networks that are realized that change. So there is no posterior over the weights, just over the predictions.
Well, I think, okay, so the argument is a bit sloppy, but Yaren's argument is basically when you do, say, a dropout in the weight space, sorry, for the hidden units, that is essentially equivalent to basically, just zero out the corresponding input weights, right? So that basically tells you you have some sort of like, say, Bernoulli distribution of the, maybe I should say two deltas, one center at 0, another kind of around somewhere. Okay, so I think this is basically just some sort of like weight space view of this dropout method. So this clearly tells you the posterior, the kind of like some sort of the induced approximate posterior is not mean field, but they still have some pathologies that we have discussed in this preprint. Okay, I'm going to tell you how we do that. So we have some very kind of say early results, and we hope to extend this result to kind of get better approximations. But first, let's start from some other definition of stochastic processes. So we've seen kind of GPs as like definition of functions as a stochastic process. So if you think about other possible stochastic process, one thing we can define is this thing called implicit stochastic process. So we take the inspiration from, for example, like GANs, where you basically just have some sort of input noise variable, which can be Gaussian, and then you path transform it through a neural network that gives you some output. The output is also a random variable, but you don't actually know like the exact analytical form of that distribution. So similarly, you can do something similar to kind of get some sort of like distribution of the functions, but you don't actually know how to evaluate the density. So it basically says that an implicit stochastic process is basically just a collection of random variables. But for finite collections, you can basically, say, sample the finite collection of random variables in this way. First, you sample some sort of latent variable z, and then you pass it through some sort of transformation, either a neural network or some other, whatever transformation you like. And then you can basically, use that to give the output f, which is also a random variable, but distributed with some underlying implicit distribution. Okay? So, as I said before, we are basically just trying to transform some sort of random variable with some neural networks or some nonlinear transformation to another neural net variable. So this Z can be finite dimensional, And in this case, it is actually quite easy to prove that the resulting kind of like the output is a valid stochastic process. You just need to check the kind of like the conditions, these two conditions in the Kolmogorov extension theorem. Okay. But also importantly, you can also use infinite dimensional Z, which basically means that, okay, I can transform a GP with some neural networks, and the output, although it's non-GP, it is still a valid stochastic process. So we have some sort of sufficient conditions to tell you how to prove this, and I won't talk about this in detail, but if you're interested, you can look at the paper. Okay, so the examples of this kind of implicitly defined process definitely includes Bayesian neural networks, because Bayesian neural network tells you I just need to sample weights, and then I use these weights to parameterize the functions. Okay, so I talk about like infinite dimensional cases of Z, which says that it also includes this kind of warp GP case. So I remember like around 10 years ago, starting 10 years ago, people want to do some sort of non-GP stuff in function space. They start to do this kind of say invertible transformation of the GP outputs to make it non-Gaussian behave. Okay, so this we call neural sampler. You can think about it as some sort of like conditional generative model that you have some sort of, say, finite dimensional Z and the parameters here for the neural networks and the inputs, and here you combine the inputs and also the latent variable to get the output. So I think this model is also branded as neural process by DeepMind people, if you have heard of that. Okay. So now we are going to do this kind of say inference of implicit processes, and maybe it will be more convenient to think about this implicit process just as Bayesian neural networks, but we are going to do this inference in function space. Okay, so we will have a implicit process regression model where you have function sample from this kind of implicit stochastic process, and then you add in some noise as a likely term to basically do regression. Okay, so it's similar to GP regression. We want to compute the posterior distribution of the function given the observed data. This is basically just Bayes' rule. If you can do that, then you can basically do a predictive inference in a similar way as to do GP predictive inference. The biggest problem here is, unlike GPs, where if you have, say, Gaussian likelihood, the posterior is also Gaussian. It is only intractable because of computation issues. But in this case, you don't even know what is the exact kind of form of the posterior because your prior is non-GP. Okay? And also, you cannot apply, say, variation inference method, because variation inference method, if you write down the elbow, it will include kind of like the KL between the approximate posterior and the prior. And in this case, because the prior over functions is implicitly defined, then you cannot evaluate the density of the prior, so that you cannot apply a variation inference. Okay? So what we did to address this problem, so we applied a kind of old technique. I think this is called the weight state algorithm in the deep learning literature. So this is from the Helmholtz machine paper back in 1995. Okay? So summary, the idea is basically saying that we are going to approximate this kind of implicit stochastic regression problem with a GP regression problem. And you will see later that that GP has a specific kernel structure. Then in the weight space, we are going to optimize the hyperparameters of that kind of implicit process. And because we are using a GP to approximate that, and that GP kernel has some specific structure, we are going to utilize that specific structure to develop a kind of scalable algorithm. Okay? So let's walk step by step to see how it works. So as I said before, we are going to approximate this kind of, say, IP regression problem with GP regression problem. So that means I'm going to define a GP prior, and I'm going to use the same likelihood term as in the IP regression problem. So to fit that, we are going to do this kind of, say, in some sense, maximum likelihood training of the GPs, which basically says that I'm going to generate some data from the IP. Okay, I'm going to sample some functions from the Bayesian neural network, and then use GPs to feed that. Okay, because we are going to match stochastic process to stochastic process, then that basically means you need to do that for any possible input of x, right? So Fortunately, because you know GP is you only need to specify kind of mean function and the covariance function, and because we do it in the maximum likelihood way, then there is actually an analytical solution for this. You don't actually need to compute that in practice. So it tells you that, okay, the optimal solution for this approximation is basically just capturing the first moment and the second moment in the function space for this Bayesian neural network. So yeah, you can do some sort of like multi-color approximation to that. That tells you, okay, I'm going to sample S functions from IP or kind of Bayesian neural network. I'm going to match the empirical mean and the empirical covariance function for that. So that gives me the GP approximation. Okay? So we have the GP approximation in hand. Now we want to optimize the hyperparameters of the Bayesian neural network. So in this case, we are doing empirical base. So because we have this kind of GP approximation model in hand, and also by this kind of inequality that tells you that the joint KL is the upper bound of the marginal KL. So that basically means if you are minimizing this joint KL, you are also minimizing the marginal KL. So at optimum, that tells you the GP marginal distribution can be used to approximate kind of like the marginal likelihood of the IP regression model. Okay, so now when we are doing this kind of say hyperparameter optimization, then we are going to maximize the marginal likelihood of the GP approximation model. And because Bayesian neural networks, you can basically just do differentiation, then you can basically just do gradient descent. Okay, so we are almost done. But as I said before, in the second part, you know, GP inference, basically computing the marginal distribution of GPs, is still n cube. We need further approximation. So now that comes in again, the kind of random feature approximation. So as I said before, because this kind of GP approximation model is basically just trying to capture the first and the second moment of the Bayesian neural network in function space, then the kernel matrix has the kind of specific structure. It is basically just kind of like the product of kind of like the delta functions, basically kind of the sum functions minus the mean, right? So this is actually kind of similar to neural networks again. So that tells you I'm going to do this kind of say random feature expansion approximation again by approximating the marginal distribution of GP with the marginal distribution of some Bayesian linear regression problem. So the idea, you can think about it roughly like this. So you have some sort of like X, some sort of black box. Let's say for this case, the black box is Bayesian neural network, and sample is from prior. So you sample multiple functions. And then you build on top a Bayesian linear regression layer that combines the results that to give you the final result f equals to the mean function plus the yeah. So this is actually different from kind of like the previous result, where if either it says that, okay, I'm going to use kind of like the GP limit of Bayesian neural networks to do approximation, or I'm going to say build a neural network that is kind of say deterministic for the previous layers, but the only Bayesian for the last layer. In this case, we are basically saying that you just put your model, which is Bayesian neural network, and then build on top of it another layer of Bayesian neural networks. Then you can basically just do this approximation and then compute approximate inference for Bayesian neural networks in function space. So now you have these. Then there are other things you may want to do. For example, for scalability, you may also want to do approximate inference on that. But I think you get the idea. The idea is essentially, if you have a Bayesian neural network, then if you want to do say function space inference, then you just put on top of it another layer of Bayesian linear regression. Okay, so does that work? So, well, we took this solar irradiance prediction data set from some previous paper, and we compared it with some two techniques. One is kind of like the exact GP regression. I believe in this case, we are using this RBF kernel, and another is basically just the Bayesian neural network, but we'll do kind of like dropout, kind of multi-hollow dropout, which is some sort of like weight space inference method. So I would say that, the GP regression has some sort of good fit at data, but in these kind of regions where it's kind of like the missing data region that you want to fill in, it has, maybe you can't see it, but it basically has kind of a very weird mean, right? It is the mean that does not fit with kind of like the ground truth. So that basically means, GP regression, when predicting the mean function is not that great comparing to Bayesian neural networks. But if you compare kind of like the error bars, the uncertainty estimation, I would say that, the function space inference method that we developed, which is a very crude approximation, works better than the kind of the variational dropout, in the sense that we have kind of like, say, better error bars that actually covers kind of like the observed data. Okay. Right. So we also run some experiments with Bayesian LSTM. That's basically why it's good to work with Bayesian neural networks, because you can apply Bayesian principles to any neural network architecture, like in this case, the LSTM. So this case, the data set CEP is kind of like a chemistry data set where the input is basically just a string represent kind of like the structure of the kernel, the molecule. Then the Y is basically you want to predict kind of the energy efficiency of this molecule. Okay? So we basically run this Bayesian LSTM model with both weight space inference, which is basically just some classical variation inference methods in weight space, and also our method in function space. And we also run some other models as well. So for example, like just a simple Bayesian neural networks with some handcrafted features that comes from, say, chemistry, intuition, and also GPs and deep GPs. So we compute the kind of like the test error and test negative log likelihood, and it seems that what? So. Okay, I think I'm almost going to the end, but I'm just going to tell you that because that is kind of like the second last slide, so that's good. Okay, so basically we are trying to kind of like leverage kind of intuition of GPs. I should say the function space inference methods to basically improve the inference methods for Bayesian neural networks. And from the previous two topics, we see that Bayesian neural networks has limits to GPs. And also, you can use the Bayesian neural net techniques to do approximate inference for GPs. So you can basically see now the GPs and Bayesian neural networks, they are actually very close friends. So I hope you enjoy this talk, and I hope you use Bayesian neural networks. Okay, I can't show you the slides to answer the questions, but if you have questions, definitely ask. Okay, I see. I think it will be kind of best illustrated in like the regression cases, right? So in regression cases, for example, in Bayesian neural networks, you have, say, P of Y given X and W, which is defined as some, say, Gaussian distribution of Y, where your mean is basically some neural network transformation, right, of X, and you have some variance here. So this term can be used to describe aleatory uncertainty, because aleatory uncertainty is basically telling you that this uncertainty is due to kind of like the randomness in data. So it's kind of like your data is noisy or kind of corrected by something. So you cannot reduce the uncertainty for that because the noise is inherent in the data. So that's kind of like aleatory uncertainty. The epistemic uncertainty is actually the uncertainty in W, which is kind of like posterior distribution P of W given E that is proportional to the data set. So I think you have some sort of like, say, Bayesian version of central limit theorem. I think it's called a Bernstein-von Mises theorem, I believe. So that tells you that if you have like an infinite amount of data, then this posterior distribution is also going to go to some sort of concentrated delta function. So in that case, when you have infinite data, then you're almost certain that your weight will be some value, which means your epistemic uncertainty actually goes to 0. So I think there are some recent work that tries to evaluate whether if you do approximate inference in weight space, for example, like Bayesian inference, can you get similar, say, limiting behavior for the approximate distribution. I think there are some positive results for that. So that's my take for like the epistemic and aleatory uncertainty decomposition.
What about the same in GP's basic? So can you
Yeah.
spread this?
Yeah, GP is pretty much the same because GP is basically just replacing this thing with some function, right? So you always have the kind of aleatory uncertainty represented in this case. Yes?
And can they model heteroscedastic noise?
Yeah, you can. So depending on how you actually set this one. But it can be a little bit tricky. So depending on how you actually do this, you might say, okay, I want to use, say, some sort of like 3 parameters at each location, right? Then you can also use, like, say, some other neural network. So let's say this is the neural network for me, and you have some other neural network to replace this time. Okay, this also represents, like, say, the aleatory uncertainty, but you also have some uncertainty in these ways.
Okay, let's thank Yingzhen again.
Okay.
Try to connect the battery, but I don't think it's correct for some reason.
Do you have an announcement for the brewery tour? What time are we leaving?
We should leave at around 6:30.
So we'll leave at 6:30.
6:30 from in front of the door.